my two favorite forms of mathematical computation really are prime numbers and probability simulations. So what's a probability simulation? Well, you can answer probability questions like, what is the probability of, say, 3 heads and 8 flips? Okay, how do we do that in 8 flips? Well, we can do it using code. And so the first thing we're going to do is we're going to import NumPy as NP. And that's going to allow us to do the coin flipping. And so we're going to do the coin flipping using the random library, using the random integers, okay, between 0 and 2, because that'll be between just 0 and 1. Okay, and we're going to count 1 as a head and 0 as a tail. And because it's just 0 or 1, it should be 50-50. And so let's go ahead and just do some coin flipping to start and run this code and verify that we are in fact getting a rotation between zeros and ones. We should never get 2. We should always get 0 and 1. Looks good. A lot of ones there. Okay. So that's how you flip a coin. And so we're going to call that a coin flip and store it. Okay. Now, if we're going to do it multiple times, well, in this case it says 8 times, then we can set up a for loop to do that. So for I in range 8, there's 8 coin flips. And now what we need to do, we need to sort of calculate the number of heads. Okay? So how do we do that? Well, how many heads do we start with? Let's say it's a count. Well, the count is actually 0, right? And we're going to keep track of them. And the way we keep track of them is we simply can add to the count this coin flipping, because it's only going to add something when it is 1, which is a head for us. It will not add when it's a 0. And so what this can show us then is how many heads do we get in 8 flips. Okay? So let's run through this code. At this point, we're not using this. This is just the definition of a coin flip. Okay, we could maybe write that as a function. But here is the important part. We start with the count of 0 heads. We're going to flip it 8 times. And I just add the coin flip, right? I add this 0 or 1. Okay, so let's do it a few times. I get 2 heads and 8 flips. Let's do it again. 3 heads and 8 flips. Let's do it again. 3 heads and 8 flips. Do it again. 4 heads and 8 flips. 4 heads and 8 flips. Kind of weird that it's counting up here. 4 would be common, right? 4 heads and 8 flips. 6 heads and 8 flips. Okay. Shouldn't do this, right? Every time we run this line of code, it runs top to bottom, and the count should start at 0. 6. What is going on here? Something seems wrong. Okay, because it should. There we go. It was counting up by ones, which was odd, right? I always like run code enough to make sure that sort of like the randomness you would expect kind of is happening. Okay, when you do this, you're going to get different results than I am, so you will know up front. Okay, so this is great. The only thing that's left to do really is now, you can see, well, you know, you may or may not get it in one trial run. We want to do multiple trial runs. So what we can do here is set up a trial, okay? And the trials are basically how many coins do we get? So we start off with none, and then instead of just showing the count, what we're going to do, it's got to be lined up outside of the for loop. We are going to basically append it, right? So we're going to append the count, because that's the number of heads in 8 flips, okay? And so what you just saw, that sequence, 2, 3, 3, 4, etc., those would now come out as a list. Well, how many trials do we want to run? That is the key. And it's really important. And so what I'm going to do is actually turn this into a function. That way we can generalize it and we can look at it in terms of the probabilities that we get when we run a different number of trials. Okay, so let's go ahead and define heads in flips, okay, right? We could do it with even different numbers. And so we'll start with n equals 3 and flips equals 8. Okay. Now everything needs to be tab. You can see the underline and colon because now we're inside of a function. So this should be on the outside is the trial. Now what we have is we want to do for each trial. So for, we'll call trial singular, for the individual trial, in what? Well, we want to do it in the range of the flips, right? Because we want to do it 8 times. Is that right? No, we haven't said yet. I'm sorry. Okay, the 8 is here. Okay, this is the flips. Okay, it's right here. This is actually going to be the total. We didn't specify. This is heads in flips, but it's also the number of trials. So the number of trials, and you know, by default, let's just do 100 and then we'll modify it. Okay, so this is actually num trials. Okay, so so basically 100 times, right? We start over with a count of 0. That should be tabbed in. Everything should be tabbed in now. And for each time we do this, right? Okay, so let's check if things are lined up correctly. Okay, we start with empty trials. Now we're going to do one. See how it's underlined? Collapse helpful with the underlines. Now trials, trails. Okay, get them the same. And we're going to start the count. Okay, start the count over each time at 0. And this part of the code we've had, it simply counts the number of heads. But after that for loop, okay, after this for loop, and if it's after the for loop, you've got to line it up actually right there. Now we add the count. So like maybe if the first one is 2, we get 2. Now where do you go? You go back here for your second trial. You start over. Now maybe this time you get 3 and you add 3. Okay? And so that should do it. And what that is going to return, it's not quite the probability yet. Let's just do it with the trials and see what we get. Okay? And then we'll adjust to get the probability next. So here we've got our function, no errors, heads and flips. And we can just run it because we've set all the parameters. And let's see if it does what we hoped, and it did not. And the reason why is because you have to be really careful with the indentation. The return is in the wrong place, right? We're supposed to get 100. The first one was 4, which is good. But if we return it there, lining up outside of that for loop, not inside, then it's going to keep going. So we try it again, run the code, and there we have a nice list. Not a lot of 3s in there, at least at the top, but it's a long list of 100. So the next question would be, how do we get the probability out of that? Well, it's what we're looking for, right, which is 3. And that's what we need to count. So before we return it, let's count it. And so we've got, it's basically, we want to look at the list. So for, I guess we could do an I again. For I in trials, and we can be better sometimes to say what it is. We're looking for the number of heads. So for the heads in trials, right, we're looking for 3. If heads is equivalent to, this is our in, which is 3, that's what we want to count. We want a new count, okay? Now this count will be we can restart a new count, okay? Because this count takes care of itself. And if you want to distinguish it, you could say it like it's a head count or something. So how many times do we get this head count? Well, if it's equivalent, we want to add 1 to it. Not the number, we just want to count how many times it's in there, right? So we're only counting it when it's equal to 3, okay? And then what we would do at the very end, we would divide the head count by the total count, which you can get in some different ways. It's simply the number of trials, okay? So that is going to give you the probability because it's the total number of occurrences, the total number of 3s out of how many there are in sum. Now this head count, I just said plus equals 1, but I didn't initialize it. So we only want to initialize it once. And I go here, and we'll just start with 0 because there could be no cases. And every time I get a match of 3, I add 1. So if there are 7 3s, I'll get 7, and 7 divided by 100. Okay, a lot of code. Let's go ahead and give it a try. And so now what it should do is return the probability. 0.13. So it said that there's a 0.13 chance of getting this, of getting 3 heads and 8 flips. What if we increase the number of trials? Okay, let's put this in here. Increase the number of trials to 1,000, and you get 0.197. Okay, what if I do 10,000? 0.225. It's going fast. As long as it goes fast, you can keep going higher. The idea is the more simulations you run, the more accurate it's going to be. Okay, now this one's taking a little bit longer. And so maybe 0.2283, it also got the 0.22. So maybe I'll just do 10,000. And if I run 10,000 a lot, you can see I'm consistently getting close to 0.22. Okay, so big question arises, sometimes 0.21. What in fact is the correct answer, right? And this is also where, if you need to be sure, the million didn't take too long, 0.218. You could even try perhaps one more. Go leave it here. And you're getting 0.218 again. Okay, that's interesting. And you could even do this multiple times, right? So just to show you, so for I in range, if you want to be more precise, like how many times do we want to do this? Maybe 10. And then what are we doing here? We've got a probability count, right? Set it equal to 0. You don't have to do this, but it can add some more accuracy. And basically, then we're going to, this is the probability count is going to be plus equal to this. And at the very end, what we want to do, and maybe we'll do it with a smaller number like 1,000, but we'll do like 20 of them or 10,000. And then what we want to do is we want to divide, of course, the probability count. We add them all up. In this case, we're dividing by the total number, which is 20. And so that can give us potentially a more robust answer. So let's see what we get when we do it in this case. That's going to be like 2 million trials. Okay, there you have that number. What's the answer? Okay, the answer is, I can tell you from pure math, it's basically 8 factorial, because we're divided by 5 factorial, 3 factorial, and this is all divided by 2 to the 8th. So it's 8 times 7, okay? This is like a choose thing. You have to have done like stats in school to know this probably. 8 times 7, the 6 factorial cancels the 3 factorial. I'm sorry, the 6 does, the 5 factorials cancel, and that'll be over 2 to the 8th. Okay, and that is the exact answer. So we press Shift Enter, 2.1875. So look at that extraordinary 3 decimal places of accuracy. In this day and age, you have a choice. You can learn probability and statistics, the formulas to be able to compute these, or you can actually run probability simulations to get the same answer. It'll even present a third option, which is my personal favorite. You can learn both.